All right, welcome everyone to our 19th lecture of the semester. So before we get started, I just want to have a quick rundown on what this week's going to be like. So today we're going to go over lecture 19, which is the beginning of the next part of class, which is going to be on integration of functions and multiple variables. And then on Wednesday, what we're going to do is we're going to be reviewing an exam. So I'm going to be going over an old exam in class, and then kind of like last time, if we don't finish it, which we probably won't, I'll post a recording that will be me finishing that off. And then on Friday, you guys can just bring in any questions you have, and it'll just be a free question answer period. I think I kind of like the system I've been doing where I take 3 questions from the chat and 1 from the live audience, and I haven't heard any complaints about that. So we'll try to do that again here. All right. So anyways, let's go ahead and get started on what we're doing today. So today's lesson is called double integrals over a rectangle. So what we're going to try to do is we're going to try to generalize integration from Calc 1 with a 1 variable function to Calc 3 with functions of more than 1 variable. All right, so let's remind ourselves what we did in Calc 1 here. In Calc 1, when we talked about integration, the definite integral from a to b of a function with the limit as n goes to infinity of the sum from 1 to n of f of xi delta x. Now, what on earth is this? Well, remember, this is the area of a rectangle. And remember that we had a bunch of these rectangles that filled up our area. Now, as you can see from the picture, and as we discussed thoroughly in Calc 1, the issue with this is that, of course, the rectangles don't always match up to the function. Like, for example, we're overestimating here, we're underestimating over there. But that's why we have n, the number of rectangles, going to infinity, because eventually those errors will taper off until we get the exact area under the curve, which is the definite integral here. So remember, the moral of the story with integration way back when is that it represented area under the curve. All right, so it's going to be very similar going forward, only we're going to just step things up a dimension. So what we're going to do, we're going to consider a continuous region, or a continuous function, excuse me, f of x, y greater than or equal to 0, although this works with negative functions as well, on a rectangular region R. So it's all the points where x can be between a and b, and y can be between c and d. Now, in the future, we're going to generalize what we're doing to more than just a rectangular area, but for now, we're just going to stick with rectangles. What we're doing here is we're trying to find the volume underneath the surface. So before we were doing area under a curve, let's step up both of these a dimension. So we'll do +1 dimension for both of these. So the next version, the dimensional version of area, will be volume. And then under, and then the next dimension version of a curve, what have we been studying recently? We've been looking at surfaces. So multiple integration is going to be about studying the amount of volume underneath the surface. So if we kind of shade in all of this right here, we want to find out how big this block is right here, how much volume that's going to take up. That's going to be our goal for multiple integrals. And kind of like regular integration, kind of like how that works for more things rather than just areas. Like, for example, you use integration in kinematics, and that's not necessarily representing an area. In the same way, multiple integrals are going to represent more than just volumes. Is it +1? It's +1 dimension. So I'm taking what we talked about up here, and I'm pushing it up a dimension. And that's exactly what the integral is going to be now. All right. So yeah, this is what I just said here. So the goal, find the volume of the solid that lies above R and under the surface. Z is, so we're just trying to find the volume of this guy here. Now, kind of like how we divided the Calc 1 area under a curve into multiple rectangles, what we're going to do is we're going to divide the new volume into a bunch of these rectangular sticks. So we have these like thin square, but then kind of tall sticks that we're going to use. And it's easy to find the volume of those. We just do length times width times height. And yeah, French fries, that's a good name for it. Yeah, perfectly straight French fries. That's essentially what's going to happen here. Are partial integrals going to be a thing? Not really. Yeah, no, it's multiple integration and partial differentiation. So we'd integrate with respect to x and z. We'll see. Well, all these questions will be answered soon. So what we're going to do is we're going to divide our region R, which remember for now is a rectangle. Sure. We're going to divide our rectangle into smaller rectangles, Rij. And what we're going to do is we're going to partition them in this way. We're going to divide up all of the x's equally. So let's say we start at A and we want to cut it up into a bunch of pieces. Then the distance from here to here is the same as the distance from x1 to x2, and so on, all the way up until we get to the distance from xn minus 1 to xm right here. All right, and we're going to call this uniform distance between all of the x's b minus a over m. And in the same way, we're going to do the same thing with the y's. We're going to have equal intervals between all of these y values right here, and we're going to call that interval length delta y. Now, once we kind of break things up like that, what do we get? Well, let's see here. So here's A to B, which are x values. Here's C to D, which are y values. And by the way, this is the domain. So this is the stuff that we're plugging in to our multivariable function f of x, y. So this is kind of looking at the top down of this picture. So here's our rectangle that we're trying to find the volume over. And we break it up into these little pieces. So this has a length of delta x, and this has a length of delta y. And you guys probably remember in Calc 1, we had left-hand Riemann sums and right-hand Riemann sums where we either chose maybe the left side to evaluate our function or the right side to evaluate our function, but then they all ended up kind of being the same once we took the limit. The same thing is going to go here. Once we define our little rectangle that we're going to find the volume over, we can pick any point in this rectangle, like maybe I'll just pick the upper right one, and we're going to evaluate our function there. So this is xi, yj. And what we're going to do is we're going to take that and put it into our function. And we're going to see how tall that is, and that's how tall our little prism or our French fry is going to end up being. And we do that for all of these different rectangles that make up this big rectangle right here. All right, so if we do this, then what's the volume under the surface? So the volume under the surface, if we use finitely many rectangles, can be approximated as the sum from j equals 1 to n, and then the sum I equals 1 to m. So we have two sums. We're summing over two different indices here. We're going to have f of xi, yj, and this is going to be the height. And then we have delta x, delta y. And this will be the area of the base. And so what we're doing, this is where we add up finitely many of these rectangular prisms. So you can kind of see in the picture here, if we had one for all of these, then that would give us this right here. Is that an I hat? Not sure which I you're talking about here. I mean, it's just I, like the letter I. It's a common index name here. All right, so we're adding up all of these rectangular prisms. Now, as you might guess, the more of these that we have, the better, because like, for example, this one seems to go a bit over our surface. So we're going to overestimate our area here. So of course, what are we supposed to do? Well, we're supposed to send the number of these rectangles, or n and m, we're going to send that to infinity. We're going to divide this up into infinitely many little pieces, and then our rectangular prisms will fit perfectly. That's what's going to be the next part. So we let both m and n go to infinity, and then we end up getting that the volume is exactly equal to this limit. And then we write down the same sum that we had earlier. Did I use, yeah, I used m for x. fxi, yj, and we have delta x, delta y. And from now on, I'm going to refer to this as delta A. So this is our tiny little area here that's going to be the base of all of our rectangles. And in the future, we're not just going to be limited to having little rectangles as our area, but we're not going to touch that today. But that'll be something for later. This just means a really tiny area dA, which is a tiny length times a tiny width. All right. So then kind of like how when we took the limit of the Riemann sum back in Calc 1, that's what the definite integral is. Well, then we're going to have something called the double integral of f over a rectangle R, and it's going to be defined to be exactly this. The limit is m and n go to infinity, meaning we're breaking our region up into a bunch of pieces. Well, I guess the limit's going there, so we don't need that. I is 1 to m, f of x, I, y, j, and then I said I was going to call this delta A. So this is effectively our new Riemann sum for our new integration. I'm a little confused by the double summation. Yeah, double summations can get pretty tricky. The way it works is what you do is you start at j equals 1. Then you go through the entire summation from 1 to m for the inside one. Then you move this up to j equals 2, and you go through the entire summation again. And then you would move this up to j equals 3, go through I through m, the x part again, and then you go all the way up until you do n, you do this one last time, and then you're done. Yeah, it's a nested for loop. So for those of you in CS, yeah, if you put a for loop inside another for loop, that's what this is going for. In fact, if you ever want to program integration, numerical integration just uses a for loop. That's all you really need to program integrals in your computer. I wish you guys could take my special Calc 2 class where we did that. But anyways, yeah, the double integral is just going to be this double sum where we add up all of these little prisms together. All right, and if this limit exists, meaning we can't actually find the integral, then we say f is integrable over R. We'll have some more to say about that later. Now, one thing I want to talk about is before in Calc 1, we had the limit from A to B here, but here they just replaced it with a single letter R. And what that means is we're going over the region R. Now, back in Calc 1, there were only two ways to go over an interval. You either go from left to right or right to left. But now we're going to find there are going to be a bunch of different ways of going over an area. Kind of like how with limits, we had just left and right in Calc 1, but then in Calc 3, we had a bunch of different directions. The same is going to be here. So a lot of times with multiple integrals, they're just going to replace it with the name of the region that you're going over, and they're not even going to tell you which way to do it, because oftentimes there are many different ways to do it. What does that say? Going over the region R. Sorry, I feel like my handwriting's gotten worse. Sorry about that. Going over the region. All right, let's go ahead and take a look at this. So let's evaluate this double integral over the region R, where R is this rectangle from 0 to 3 with x and 0 to 4 with y. So it's kind of the base of this wedge right here. All right, now let's see. So this, remember, the interpretation of a double integral is the volume under a surface, right? So if we want to get this double integral, we can find the volume that's going to be under this surface right here. So you can imagine that this is z is 8 minus 2y. We're finding the area of the volume under that. All right, so how do we find the volume of this triangular block? Well, what we do is we do the area of the triangle times the thickness of the wedge. So the area of this triangle will be 1/2 times the base, which is 4, times the height, which is 8, and then we multiply that by how thick it is, which is 3. All right, so we have 1/2 times 4 is 2, times 8 is 16, and then times 3, that'll give us 48. So it turns out that this double integral is going to end up being 48. That's going to be the volume underneath here. Okay, well, that's fine, but that's kind of like the equivalent of like finding the area of a triangle using an integral. Like you could do that, but that's not really the point of them. The point of them is to find volumes under things that are irregular and kind of different. So how are we supposed to do that? Well, let's talk about that. Next, what we're going to talk about is iterated integrals. And this is how we're going to integrate over things that aren't really nice looking. That. So to calculate the volume of the solid given in the definition of the double integral, we can take the solid, slice it into thin sections perpendicular to the y-axis, and then add the volumes of each slice. You may remember, if you had me for Calc 2, where we found the volume of different shapes by breaking it into cross sections that had a very small thickness. That's exactly what we're doing right here. So take that mentality that we had in Calc 2 when we were doing volumes and apply it right here. That's exactly what's going on. All right, so let's take a look at this picture right here. So what they're doing is they froze a y value. So they froze a particular y value, and they looked at the area under this curve with respect to x. So all of this is happening in the x direction, and our y is constant here. So what does that look like in terms of our integral? Well, what we're doing is we're doing the integral from a to b of f of xy dx. And so we're doing that. And y here, this is going to be constant while we're doing this integral. Then afterwards, what we're going to do is we're going to integrate all of these volumes together from c to d. And we're going to do that with respect to y. So effectively what the second integral is doing is adding together all of these little slices of cheese, as Marissa's saying. We're adding all of those together, and that's going to give us our total volume. So this right here gives us cross-sectional area, and then the whole thing would be adding cross sections together. So that's what's going on with this integral right here. And so you'll often find that we can do an integral with respect to x, and then we could do so with respect to y. Is this only for when the surface is uniform? If by uniform you mean continuous, then yes. And we're going to talk about that in a few minutes here. So by all means, what I could have, instead of doing this, freezing the y value and doing the x integral, I could have also frozen x and then done this with y as well. So we'll talk about that in a little bit, like deciding which order to do things. So this is called the iterated integral when we do first the integral with respect to one variable and then with respect to another variable here. All right, and now one thing that's a little bit strange about this, or I don't know if it's strange or not, but it may take some getting used to, is that we need to do the integral on the inside first, and then we do the outer one. So whichever thing is listed first here in reading order, that's what we're going to do first. Right here. All right, so let's go ahead and practice this. Let's go ahead and try it out for something that isn't just a shape that we can use a formula. Oh, does someone have a question?
I had a question, which was, so you're taking that little slice, right? Is it just that slice that's generalized to that whole y interval, or like, do you know what I'm saying?
Well, so this is at one kind of random y value. So this is the area of a cross section at a particular constant y value. And what we're doing is we're adding together all of these slices when we do the integral with respect to y. So we do the integral with respect to x to build the cross sections, and then we do the integral with respect to y to add together all of those cross sections.
Gotcha. Thank you.
No problem. So let's try a numerical example here. So let's evaluate the iterated integral. 1 over the square root of 3x plus 4y dx dy. Now, this is where double integrals begin to have things in common with partial derivatives, is that when we're doing the x integral, remember what I said earlier, when we're doing the x integral, y is a constant value. We need to hold y constant so we can go back to Calc 1 and do an x integral here. So when we're doing this, oh no. My computer is getting really finicky with inputs. No, I don't want to do this. There we go. Sorry about that. Yeah, my USBs aren't connecting very well. All right, anyways, so we want to do the x integral first, but when we're doing the x integral, anything with a y is constant. You can effectively imagine this as 1 over the square root of 3x plus some constant. Now, if we were back in Calc 1 and we needed to do that, then the way we're going to do this is we're going to do a u sub. So I'm going to do u is 3x plus 4y, and then I'm going to do the x derivative here. So du will be 3 dx. Now, we don't have an extra 3 laying around here, so I'm just going to divide by 3. All right, so then when I plug in my u, going from x is 0 to x is 3, this is going to be 1/3 1 over the square root of u du, and then we still have this y integral to do later. All right, now let's see here. The integral of u to the negative 1/2 will be u to the positive 1/2, and then we divide by 1/2, which is multiplying by 2. So this will be the integral from 0 to 4, 2/3 square root of u from x is 0 to 3. And remember, we still have a y integral left over to do. All right, let's substitute back in for our u here, so we can plug in our bounds. So this is the square root of 3x plus 4y from 0 to 3. Right? God. Okay, I need to stop touching this. Isn't it negative? I don't think anything should be negative here. Yeah, because we had u to the negative 1/2, and then I raised that to u to the positive 1/2, and I divided by 2. So I don't think there should be a negative in here. And then finally, I'm going to plug in x is 3 and x is 0. So this will be, very careful, don't touch the board. We got to do 0 to 4, and then I plug 3 into here, and I have the square root of 4y plus 9. And then I subtract, and I plug 0 in here, which will just be the square root of 4y. All right. So that's my x integral. And then now all we have left are y's. And if you did this properly, you should only have y's once we get rid of the first integral. So now I'm just going to do the y integral of this. Doing the integral of the square root of something times y plus a constant, all we're going to do is just do the normal power rule, and then we're going to divide by this number here. Okay, so we have the 2/3 from earlier. This is going to be square root of 4y plus, or sorry, not the square root. It's going to be this to the 3/2, 4y plus 9. I divide by a 4 because of this 4, and then I divide by 3/2 because of the power rule and get this. So all of this stuff is going to be times here, and then we have 4y to the 3/2, and I have the same stuff happening there. And this will be from 0 to 4. All right, so if I have some fun with fractions and cancel these out, we end up with 1/9. And then now I'm going to plug in 4 in for here. So let's see. I'm going to have 16 plus 9 is 25. The 3/2. And then I'm going to have minus 16 to the 3/2. And then I'm going to subtract when I plug in 0. So I subtract 9 to the 3/2. And I would technically add 0 to the 3/2, but that's it. All right, now thankfully all of these numbers are nice to do 3/2 powers with. This is 125, this is 64, and this is 27. And if we do this, let's see, 61 minus 27, we end up getting 34/9. All right, and this is going to be my, how did the 1/4 get there? You're talking about this 1/4? This 1/4 came from integrating this. I integrated something with a constant times the variable underneath. And when we do that, we need to divide by whatever the variable was. So I divided by 1/4. Yeah, Michael has the right idea. It's technically like a little mini U sub. So I kind of, I like to just kind of skip the U sub there because it's yeah, it's usually not too big of a deal. But yeah, anyways, that's how we end up getting the 1/9 down there. Okay, now for you guys, try and practice your skills here. Try to do the integral the other way. So try to do the integral with respect to y first and hold x constant, and then do the integral with respect to x. And lo and behold, if you do that, you'll actually get the same thing. You'll get 34/9. And if you think about what the double integral is, this isn't really that surprising because we're finding a volume, right? It doesn't matter which way you find the volume, it's the volume of an object, so it's got to be constant. So it doesn't really matter which order we do it in, we're going to get the same answer, so long as our function is nice enough. All right.
Do you ever find it's easier to do one way, one variable for the other?
Yes, absolutely. Yeah, I'm going to talk about that for my next problem here. All right, so the name of the theorem that guarantees that we can do this in any order is Fubini's theorem. If f is continuous, so we need f to be continuous for this to work on this rectangle, then we can do the integral in any order we want. So we can do c to d, or we can do the x part first, so dx and then dy, or we could do the y integral first and have that be on the inside. Either way is fine, so long as this is going to be a continuous function we're looking at it. All right, let's see here. So let's take a look at this. So while the order of integration of a double integral may not affect the value, the ease of integration may be dependent on the order of integration here. So why don't we try to do this one? So why don't we try to do the integral with respect to y here first, and then we'll do it with respect to x. All right, so let's see here. For this, might try, maybe you could try a u sub for this. I didn't finish copying the formula. It's just you could do the integral in either order here. So you could do the y integral for the x, or the x formula, and then y. All right. What did I write at the top? Oh yeah, it was this. Sorry, I went too fast. My camera doesn't get as much stuff at home. All right, let's do this one. I'm going to try to do a u sub with this. Let's see how that goes. So we're going to do u is xy plus 1. Now remember, I'm doing a y integral right here. So I have du is going to be x uy. All right, now I don't have an extra x laying around in here, so I'm going to divide that over. So I'm going to have du over x is dy. All right, now let's see here. I have just a y up here, so what am I going to put down for that? Because I know I could just put u for the bottom. What am I going to put up here? Well, if I look at u minus 1 over x, that's going to be y, because I subtract 1, and then I divide by an x here. So if I want to write just y, it's going to be u minus 1 over x. All right, let's see what our double integral turns into. So we haven't done x's yet, so that's going to remain the same. And then we have y is 0 to y is 1. Now on the top, we had u minus 1 over x. On the bottom, we're going to have u squared. And then remember, we have an extra x here. All right, so this is what our integral turns into. Slide this carefully. Now we can move the x's outside the integral with u's in them. So I'm going to do that now. Now wait a minute, how can I just move these x's outside without being integrated? It's because x's are a constant with respect to u, or what u used to be, which is a y right here. So we could just freely move those out without any issue whatsoever. All right, and then we're just trying to do the integral of u minus 1 over u squared right here. Actually, wait a minute. Yeah, no, okay. So y is 0, y is 1. All right, so with this integral here, what we can do is we can split it up. So we have u over u squared is 1 over u, and then we have minus 1 over u squared here. Where did the x in the denominator come from? It came from this when we did our substitution back here. All right. So now we have this, and that's an integral that we can do. So we have 0 to 1, and then we have 1 over x squared times natural log of absolute value of u plus 1 over u if we do the power rule there. Okay, so now let's convert back, and let me move over here so we have some room. So we have 0 to 1, 1 over x squared, and then we have natural log of absolute value of xy plus 1 plus 1 over xy plus 1. And we're doing that from 0 to 1 with y's. So now if we plug this into here, what are we going to get? Well, let's see. We're going to have natural log of absolute value of y. Oh, sorry, we just did the x integral, right? So it's going to be, wait, no, this was dx. Okay, yeah, that was dx right there. Yeah, thank you. Yeah, that's what I meant. Okay, so this is ln of x plus 1 plus 1 over x plus 1 minus, if I put 0 in for the y here, I'm going to get 1. Okay, so now my goal becomes to integrate 1 over x squared times ln of x plus 1 plus 1 over x plus 1 minus 1 dx. Now, these ones won't be too bad, and by too bad, I mean we can kind of just do partial fractions with those. ln of x plus 1 over x squared, there may be some trick to doing that one, but that one's going to be really hard to do right here. We do u as x minus 1. Yeah, I mean, so the point is that this integral is a frowny face, right? This integral, even if we knew exactly what to do for this, it's not going to be that great to do. And maybe you could be like, oh, we shouldn't have done u sub, maybe we could have done something else. We actually could have done something else. We could have done partial fractions with this, because technically you could do partial fractions with this with respect to y right here. But that would also be really annoying, and that would also give you a similar integral down here. So what are we supposed to do? Well, we don't need to call upon an integral calculator, fortunately. All we need to do is just flip the order of integration. Why don't we just do x first instead of y? Make sure we don't pull this out. Okay, so why don't we try this again, only this time we're going to do x first. So I'm going to do the integral from 0 to 1, 0 to 1, y over x, y plus 1 squared dx dy. That's what I'm going to do here. Nth dimensional integrals, yeah, we'll come to those soon. Not today. Those will come up. All right. So anyways, let's take a look at this here. So I want to do this integral with respect to x, right? So I'm actually going to try the same strategy. I'm going to make u be my denominator here. And this one's actually going to work out better because then I do du. I do this with respect to x and get y dx. And that's good because I do have a y dx right here. So that means that this is going to turn into 0 to 1. X is 0 to x is 1 of du over u squared dy. And now this is a much easier integral to do than what we had last time. We have 0 to 1, and then we have negative 1 over u from x is 0 to x is 1. All right, and then we can go ahead and plug in, isn't it dy dx? Well, I changed it to be dx dy because it's going to be easier. And we can use it, use Fubini's theorem. Shouldn't it say du dy? It does right here. Duty. Yeah, it says it right here. All right, so then let's go ahead and plug back in for our substitution. That's y plus 1, 0 to 1. And then we can plug this in here. Now we have negative 1 over y plus 1 plus 1. Okay, where did we get this from? Well, I plugged 1 in for my x, and I got 1 over y plus 1 there. And then I subtracted, so it's going to turn into a plus. I plugged in 0 for my x, and then I just got 1 over 1. And now we can do this integral, and this is a very easy integral to do with y. Oh my God, I knew that was going to happen. There we go. Okay, so we end up with negative ln of absolute value of y plus 1 plus y from 0 to 1. And if we do this, we have negative ln of 2 plus 1. And if we plug in 0 for both of these, it's just going to be 0. So we end up with negative ln of 2 plus 1 right here. All right, so that integral was much easier to do than the one on the previous page. By the way, one way to do super hard integrals that they don't teach you in Calc 2 is to do this. So we know that the answer to this integral is negative ln of 2 plus 1, right? So that means that we know that this integral will end up being negative ln of 2 plus 1. And we don't even need to evaluate this anymore. We know that once we do this, it'll end up being the same as the other one, and it'll end up being this. So this is a very kind of weird and advanced technique for doing single variable integrals, is you set up kind of a matching double variable integral and then try to do something like this. I wouldn't recommend doing that. It's really hard to do it that way. All right, let's do maybe 1 or 2 more examples here. I'm sorry about the time here. I think we're probably going to run out of time. Later. Find the volume of the solid in the first octant enclosed by z is 4 minus x squared and y equals 2. All right, let's draw this. So here's y is 1, y is 2, is right here. All right, z is 4 minus x squared, so we draw a parabola in the zx plane. And since y isn't mentioned at all, we can kind of just extend this in the y direction until we hit y equals 2. So we end up with this as our shape right here. All right. Now what we want to do is we want to find the volume of this. Remember, double integrals, they represent volume under a surface. So what we're going to do is we see that our surface is z is 4 minus x squared. So that's what we're going to be putting into our double integral. That's the thing that we have up here. And then we have a choice. We could do this with respect to x first, or we could do this with respect to y first. Now, I definitely want to do this with respect to x first because this has only an x in it. So I want to get rid of the x first and then just do the y part. So I'm going to do x. And let's see. So when does this hit the x-axis here, well, why don't you guys tell me that? I haven't asked too many questions today. What x value are we going to hit the x-axis at? There we go, 2. So the bounds of my integral for x will be from 0 to 2. And then my lowest y value to my highest y value will be 0 to 2. What is the first octant? It's where x, y, and z are all positive. So that's why we didn't extend this thing back behind here, because we would have a negative x value right there. All right. Let's go ahead and do this. Let's do the x part first. And there's no use sub required for this. It's going to be 4x minus x cubed over 3. And then from 0 to 2, we still have our y's. Let's see, I put 2 into here and I have 8. And then I put 2 into here, I have 8/3. 8 minus 8/3 will be 16/3. All right, so this ends up just being a number, and that's kind of nice because we didn't have any y's in there. So now we're just integrating a constant with respect to y. And it kind of makes sense, right? Notice that this isn't really changing in the y direction. We're effectively kind of just finding the area right here and then bring it along a distance of 2. So if we were to integrate this, we have 16/3 y from 0 to 2. So then we're going to end up with 32 over 3, our volume right here. So the moral of this story is this: if you're ever missing a variable in your multiple integral, then do all the other variables first. And then all you have to do is multiply by the length of this interval. So technically, we just multiplied 16/3 by 2 right here. So that's kind of a trick to save time if you're missing some variables in the beginning here. All right. So, and then this could be generalized a bit. So let's say, sorry guys. Okay, so let's say that our function of x and y can actually be split up into a function of x times a function of y. So that's not always going to be possible. Like, for example, if you have sine of x plus y, there's no reasonable way to, well, can you do sum to, no, I don't think you can do sum to product reasonably to split that up. But yeah, you can't split this into something with x times something with y right here. But so that's not good. X that out. But on the other hand, if we have maybe like x squared y cubed, your y cubed would be your h of y, and your x squared would be your g of x. All right, so what are we going to do here? How can we save time with this integral? Well, let's say we're doing a to b, c to d, and we're doing the x variable. Now, since we're doing an integral with respect to x, anything with y's in it is a constant, right? So with respect to this inner integral, I can move the y out. So this is c to d h of y, and then I have the integral from a to b of g of x dx. And then I have my dy here. Now let's take a look at this really carefully. What is a definite integral? We're doing the definite integral from a to b of g of x dx, right? Well, this, oh, it's not negative. This is just a number, right? This number is the area under this curve right here. But this is just a fancy way of writing some kind of constant. So when we get this, we can move that constant out of this integral. So then we have the integral from a to b of g of x dx times the integral from c to d of h of y dy. So when we have a function of x and y that we can split like this, then we can actually just do the integrals separately, and we can just multiply their answers together. Technically, we did that over here in a really stupid way. We did 4 minus x squared as our g of x, and then 1 as our h of y. And the integral of 1 from 0 to 2 is 2. That's why we just multiplied this by 2 here. So technically, we've already done this. But it can be used in more helpful scenario is kind of like this one. So let's see here. If we want to do this integral, but we won't be given two formulas we have to recognize they can be split. Yeah, that's right. So for example, this one, it's not immediately obvious that this can be written as something with x times something with y. But let's see if we can maybe make it that way. Let's see, exponent rules dictate that this is going to be e to the x times e to the y. That's what addition does with exponents. But then what I can do is I can regard my h of y as these combined right here, and then my g of x can just be this. So this is g of x, and this is h of y. So what I do is I split my integral into two pieces. I have the g of x part, and then I have the h of y part. All right, and then now I don't even need to do any kind of double integration. I just do two calc 1 integrals here. Well, this one's kind of calc 2. If I do the integral of this, I get e to the x, 0 to 1. And if I plug in 1 and 0 here, I end up getting e to the first minus e to the 0, which will be 1 right here. Does this only work if you're multiplying? Yeah, because the whole multiplying thing was how we proved that this worked, because this was multiplied by that as a constant, so we can move that out. So yeah, they do need to be multiplied. All right. Oh, this has been a while since we've done an IBP in here. I think we did one maybe at the end of the first section. I don't remember. Let's go ahead and review how to do this. So I'm going to use tabular method of doing this because it's a polynomial times an exponential. So I have my y here, my e to the y here, and I do derivatives, and then I get to 0 here. I do integrals, and I keep getting e to the y. And then remember, we multiplied down diagonally by these and alternate sign right here. So we end up with this, and then this is going to be times y e to the y minus e to the y. All right, so we multiply those two, and then we subtract that here. All right, and then I'm going to go ahead and plug in 1 right here. So let's see, we have e to the y minus, or e to the 1 minus e to the 1. That's actually just going to be 0. And then we plug 0 into here. We get 0 here and 0 here, which will be -1. But remember, we subtract the second value. That's all just going to end up being +1. So we end up with e minus 1 as our answer for this integral. So the moral of the story is we didn't need to do this as a combined iterated integral like we did with the previous problems. We could just split this up into two different pieces. Yeah, Jessica, what's your question?
I had a question. Like, I sent you an email this weekend. But like, you know how the last problem we did was the volume of the solid in the first octant? There was a problem similar to that on the Kronos, like 17 or something. And I was wondering,
there was?
I don't know, it said find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate plane.
Oh, you don't need to do multiple integrals for that. You can do that as a minimization or maximization problem. So you set up a function f of x, y, or maybe f of x, y, z to maximize, and then you include the constraint in there. So you don't need to you don't need to do any of this for that.
Okay, did we do problems like that in class, or we didn't?
Well, they're applied ones, so you kind of have to make up the function on your own and then do what we did in class.
Okay. All right, thank you.
Yeah, no problem. All right, and let's see. Let me stop my recording here.